Ancient people saw them as messages from the gods, as supernatural winds that blew from the realm of spirits. Modern science has linked these polar light shows, called auroras, to vast waves of electrified gas hurled in our direction by the sun. Today, researchers from a whole new generation see this dynamic substance, plasma, as an energy source that may one day fuel humanity's expansion into space. What can we learn? And how far can we go? By tapping into the strange and elusive fourth state of matter. A small cadre of scientists has come to Fairbanks, Alaska, to realize what may seem an impossible dream: to revolutionize space travel.
Cool.
Dr. Ben Longmire and his team from the University of Michigan have designed a whole new type of rocket engine that promises a faster and more efficient way to get around in space. They are here to test components of this rocket by sending them aboard helium balloons to an altitude of 30 kilometers into the harsh environment of space. Above the North and South Poles, conditions are about as harsh as you can get. Our planet is bombarded with a steady stream of charged particles from the sun. Earth's magnetic field accelerates and channels them, turning the night into a spectacle of color. While most astronauts train to live and work in zero gravity, or to move around in bulky spacesuits, these would-be space explorers are preparing to negotiate some of Earth's harshest environments. Once they launch their payload, it will rise slowly into the upper atmosphere. After drifting through the night, above 99% of Earth's atmosphere, the payload will detach from the balloon and parachute down to the ground. The team must be prepared to retrieve it across a large stretch of Alaska's snowy wilderness. To understand the revolutionary nature of the idea they are pursuing, we go back to the dawn of rocketry. In over 100 years, the technology of a rocket has hardly changed. Fill a cylinder with volatile chemicals.
Contact! Yes, contact!
Then ignite them in a controlled explosion. The force of the blast is what pushes the rocket up. Nowadays, chemical rockets are the only ones with enough thrust to overcome Earth's gravity and carry a payload into orbit.
Testing concepts for the future.
But they're not very efficient. The heavier the payload, the more fuel a rocket needs to lift it into space. But the more fuel a rocket carries, the more fuel it needs. One of the fabled Saturn V rockets of the Apollo era, for example, weighed in at 177,000 kilograms. Filled up with fuel, it weighed almost 16 times that. The space shuttle, with maximum payload, weighed about 100,000 kilos. Add tanks and fuel, and it lifted off at 2 million kilograms. Regardless of weight, for a spacecraft to escape Earth's gravity, it must reach a minimum speed of 40,000 kilometers per hour. The energy needed to do that meant there wasn't enough fuel for a sustained acceleration to more distant planetary shores. Most missions beyond Earth have relied instead on their initial launch speed to coast to their destination. The twin spacecraft of Voyager, for example, did not have enough speed to reach their current positions at the edge of the solar system. To give them a boost, flight planners sent them into Jupiter's gravitational field, using its pull to slingshot them out to Saturn. Voyager 1 used Saturn to accelerate to almost 63,000 kilometers per hour. Voyager 2 got further assists from Saturn and Uranus. Ben's rockets promise far greater gas mileage than traditional chemical rockets, but with enough power to reach distant targets more quickly. The idea is that once in space, his rockets use electricity to create a weak force, which over time can accelerate them to very high speeds. They run on the same fuel that nature uses literally to power the cosmos. Not long after its explosive beginnings, the universe was awash in vast stores of hydrogen gas. But even as the universe continued to expand, gravity drew clumps of matter into ever denser concentrations. The earliest stars took shape, immense balls of hydrogen gas hundreds of times the mass of our Sun. As they contracted inward, they heated up and ignited. Intense radiation now began to flow through the voids. That had the effect, all through the universe, of stripping electrons away from the primordial gas. The universe became filled not with solids, liquid or gas, but with a fourth state of matter, plasma. On our planet, plasma occurs only in rare circumstances. In a hot flame, a bolt of lightning, or in a blown electrical transformer. Made up of negatively charged electrons and positively charged ions, plasma is in most cases electrically neutral, since the charges balance each other out. That led the physicist Irving Langmuir in the 1920s to compare it to the clear liquid plasma that carries blood cells through our bodies. The development of radio led to the discovery, high above the Earth, of a natural plasma ceiling, the ionosphere. It hovers above us, reflecting some radio frequencies and absorbing others. Its importance became clear when engineers noticed that radio waves could, under some conditions, travel beyond our line of sight. They discovered that signals could be bounced deliberately off this conducting layer in what's called skywave propagation. In World War II, a whole new age of global communications came of age when radio was used to execute complex worldwide logistics of troop and ship movements. The presence of the ionosphere is due to a steady stream of charged particles, or plasma, that comes from the sun. A spacecraft with complex computer components must be able to survive constant exposure to these particles. As part of their design process, Ben and his team want to test some of the specialized components of their rockets in the plasma-filled environment of our upper atmosphere.
I got it down because I think it's just the sun.
Yeah, I think that one's okay.
Alright, yeah. I'll wrap the middle one though. Or I can just wrap it.
These components will be mounted on a simple frame attached by rope to a high-altitude balloon.
Hold on, they're not oriented the same.
Do you do the CO2 in the radio?
The frame is also outfitted with an array of novel sensors to take independent readings. One holds a colony of bacteria.
The idea is that the bacteria itself can detect radiation. So it mutates in a certain way or in a very known way that when you send it into an environment with a lot of cosmic rays and a lot of perhaps X-rays from the aurora itself, it mutates. And so we'll detect sort of the level of radiation that it's exposed to by looking at these mutations after we recover the bacteria from flying it to the edge of space in these balloon capsules.
Jordan, you got the camera or wait a second.
Another is a series of tiny GoPro cameras converted to record the intensity of infrared and ultraviolet light, normally hidden from the human eye.
We want it to kind of puff up so we know it's replaced all the air.
The team uses argon gas to insulate instruments against the cold, with chemical packets added for warmth.
For this test, we're doing normal video, version 70 firmware.
They stabilize the frame with tiny gyroscopes and outfit it with GPS devices for tracking.
Cool.
This team is doing much more than just designing instruments to survive a rain of charged particles. Their goal is to design spacecraft that actually harness the explosive properties of plasma. Unlike most matter on Earth, plasma conducts electricity and responds to magnetic fields. In space, these properties influence the formation of structures like galaxies and nebulae. And they play a role in some of the most violent processes in the universe, such as the formation of a black hole It forms in the wake of a giant star's death when matter collapses into its core. It swirls in along what's known as an accretion disk. Magnetic fields take shape on the disk, rising and twisting around the polar regions. They draw huge volumes of plasma up, then shoot it out at high speeds. These plasma jets can extend far beyond the largest black holes. You can see them blasting continuously from the centers of galaxies, reaching thousands of light years into space. Studies of one giant nearby ball of plasma show what a complex and volatile substance it can be. In the core of our sun, high heat and crushing pressures cause hydrogen atoms to crash together. That sets off a nuclear reaction in which hydrogen atoms fuse into heavier ones like helium and carbon, generating heat. This heat slowly rises to the surface of the sun in vast plumes of plasma. You can see evidence of this process, called convection, in a pattern of ever-evolving blobs known as granules. They are like the tops of thunderstorms. Even as energy builds within, the sun's gravity and density can stifle its escape. What carries it out are magnetic fields. They twist and wrap around, channeling energy to the surface. The fields can power immense loops of hot gas, about 60,000 degrees Celsius, then rise up from the solar surface and fall back. The largest eruptions, called coronal mass ejections, can reach up to 3 million kilometers per hour as they hurtle out across the solar system. They can literally slam into Earth's own magnetic field. Because solar particles are charged, a portion follows the orientation of Earth's magnetic field lines. Finding an opening at the poles, they race down into the atmosphere. You know this is happening when you see the beautiful lights of the Aurora Borealis in the far north, or the Aurora Australis in the south. They appear when charged solar particles collide with oxygen molecules in the upper atmosphere, causing them to glow blue, red, and green depending on altitude. Flying through a zone called the thermosphere, some 350 kilometers above the Earth, astronauts in the International Space Station watch in awe as the aurora shimmers, framed by the glow of stars and cities at night. Back in Michigan, Ben and his team have set up a lab to pioneer a whole new generation of plasma rocket engines. The lab recalls an earlier period of space exploration. It features a giant vacuum chamber built in the 1960s in hopes of winning a contract to test Apollo moon rovers.
As part of all the facility upgrades that Roland has done for the X3, some of these should be able to...
The chamber has given this small university team the ability to accelerate their research into the physics of plasma and rocket engine design.
The tubing for the gas lines don't affect the thrust measurement. So by having these extraordinarily flexible lines, these wires...
They are actually part of a larger community of plasma rocket scientists within NASA and within private companies like Ad Astra of Houston, Texas. Because plasma does not occur naturally on Earth, the challenge is to create it, then harness it. The teams inject a gas, commonly argon, into a chamber. They bombard it with radio waves, which strip electrons from the gas and turn it into a plasma. The soup of electrons and ions accelerates as it moves through a magnetic field generated by superconducting magnets. A second radio blast heats it up to 1,000,000 degrees Celsius. That's enough to blast it out and propel a spacecraft. The idea of using plasma to power rockets is not a new one.
Over here? Yeah. Okay. 3, 2, 1.
Go! No spin, look at that.
The Polish physicist Stanislaw Ulam is said to have been inspired by atom bomb tests in the 1940s. He speculated that waves of plasma from small nuclear detonations could propel a spacecraft to extreme speeds. In the 1950s, that idea animated dreams of exploring the solar system in spacecraft like this 360-ton Mars-bound vehicle. The idea gained funding in the Orion project, with the idea of driving a spacecraft with nuclear pulses and landing on Mars in only a month. Concerns about radioactive exhaust helped doom the project. Plasma rockets, energized by nuclear reactions, were revived in the Daedalus and Nerva projects of the 1960s. And again at the beginning of this century, as part of a proposed journey to Jupiter's moon Europa. Rising costs killed that mission. Newer plasma rocket concepts have switched to solar energy to power their engines. Among the most ambitious, the Dawn mission was sent into orbit aboard a Delta II rocket in the year 2007. It then headed out on a 10-year mission to the asteroid belt. It uses only about 10 ounces of xenon gas fuel per day. With engines designed to fire for over 2,000 days, over time, it is expected to gain an additional 38,000 kilometers per hour. After a gravity assist from Mars, Dawn arrived at the asteroid Vesta in 2011. It spent a year mapping its surface and seeking clues to its interior structure. Now headed for Ceres, a dwarf planet located within the asteroid belt, Dawn will be the first probe ever to visit. Made up of rock and ice, Ceres may well have an internal liquid ocean. It takes us back to the formation of the solar system, when objects like this grew and developed into planets. Long-range missions like Dawn are just one of many uses for plasma rockets.
So NASA launches spacecraft with ion engines and Hall thrusters on board. Almost every new geostationary satellite that a company will invest in and put up in orbit will have some sort of electric propulsion device on board to do station keeping, so to do little changes in attitude and maneuvers to keep it in its geostationary orbit.
NASA is planning to use a plasma rocket to do some even heavier lifting as early as 2016. Flying at an altitude of 350 kilometers, the International Space Station whips around the Earth every 1.5 hours. To stay aloft, it must maintain a speed of 28,000 kilometers per hour. But its solar panels and crew modules smack into so many tiny molecules in the upper atmosphere that it gradually slows down and loses altitude. To stay aloft, the station uses up around 4,000 kilograms of fuel per year. That fuel must be flown up from Earth, which in turn reduces the amount of food, water, people, and equipment that a resupply mission can deliver. The idea is to use a plasma rocket to help boost the station to a higher altitude, powered by electricity generated by solar panels aboard the station. Plasma rocket builders like Ben hope to one day scale up the technology to power a long-range human mission. After weeks spent accelerating in Earth orbit, the rocket would make a break for Mars. Cutting flight time from a year to several months would lower costs and crew hazards. In the meantime, Ben has his sights set on what he sees as an even larger revolution in space exploration. Using plasma rockets to power a fleet of miniature spacecraft. Ben's rockets are so small, that they can fit into your carry-on luggage.
So here we have a CubeSat. This is a small spacecraft. Its total mass would be something on the order of 5 kilograms, so it's about 10 pounds. It's 30 centimeters by 10 by 10. This is considered a 3U spacecraft, so 3 units of 10 by 10 by 10. And we'd like to send this small spacecraft up with one of our new propulsion elements in it. This is a rapid prototyped propellant tank. So we would use this tank to store our propellant. Initially, we have an idea to use a very simple propellant.
The NASA craft Dawn uses the inert gas xenon as fuel. Ben's team has turned to another type of fuel that's more compact, can store more energy, and is less volatile. Distilled water.
We'll ionize that propellant with radio waves, and that'll form a plasma. So we'll strip off some electrons. We'll have the sea and collection of ions and electrons. We then accelerate, we superheat that plasma, and then we accelerate it through a magnetic nozzle. So the plasma never touches a material boundary, so it doesn't cool off. All of that would be contained within this spacecraft. So the propellant tank is designed to be the right size and dimension, and we'd have a propulsion module within the CubeSat itself. This is an early prototype circuit board, just this component that would sit inside of the CubeSat, and it would take the DC power from some sort of solar panel on the surface, change that DC power into our radio waves that we need to ionize the propellant into a plasma. We then shoot this plasma out the back, and we apply just a little bit of force. It's not a whole lot. It's something like the force of a sheet of paper sitting in your hand. And because there's very little drag in space, we use this small amount of force applied over a very long amount of time to accelerate to very high velocities with the spacecraft. And so if we do that, we can send these little micro spacecraft, nanosats, we can send them to places like the moon, we can send them to Mars, and someday we'd like to send them even as far as Jupiter and maybe put some little sensors on board and be able to detect possible life on some of these moons out near Jupiter and Saturn. So instead of a $1 billion NASA mission to explore the moons of Jupiter, we can get away with something like $1 million spacecraft mission with one of these small sats. And so that's the real advantage, being able to have a very low barrier to entry financially and technologically to make some of these innovations really quickly, go fly them, go fly often, and make these discoveries.
Already, hundreds of micro, nano, and even smaller satellites are in orbit. They get into space by piggybacking on commercial or government launch vehicles. Their missions range from communications and intelligence to Earth imaging. Because the cost of building them is so low, the number of tiny satellite missions is on the rise.
Yeah, there was no other satellites up there.
With an array of plans already materializing, the team is tapping into satellite traffic and orbital communication systems.
Looks like we won't quite go over to the ground station here.
Ben and his team plan to start with a series of orbital missions, then to go interplanetary.
So you can see here some of the technology we're working on. So
Ben imagines that his little group could take center stage in a project that space visionaries have long seen as essential to the quest to extend our lives and minds across the solar system.
Guide the plasma out through a magnetic nozzle. Recently, we also envisioned that a large cadre of these small spacecraft could form what would be an initial interplanetary internet. So you can think about a large number of these spacecraft orbiting the Earth, orbiting the Moon, being spread out between the Earth and Mars, and providing little data relays between all of those positions so we can get a lot of data back and have the beginnings of a real solar system internet going beyond the Earth.
Well, as long as it's beating like that, you have to shorten it to get into the Earth.
Back in Alaska, their latest payload has flown all night at an altitude of over 100,000 feet. Then, in the low air pressure, the balloon burst and the payload parachuted to the ground.
Point at it.
Yeah, so this is our Garmin GPS. We've got a waypoint.
From GPS signals given off by the payload, they have a good idea of where it is.
Plugged in the coordinates, and this is going to be an all-day adventure. It sounds like we've got 5 miles.
But that doesn't mean retrieving it will be easy.
It's going to be rough going at
No,
the
we're
end.
right here. And you see where it says Sled Road?
Yeah.
That's the trail we're going to be following down.
Oh, wow.
John knows where there's a cutoff that's going to take us off that Sled Road over to Dune Lake. And this little pond or lake right here, just to the west, maybe about a mile north, is where we believe the target is.
The payload to be, yeah.
So we're going to come down here, we're going to look for the turn, head out to Dune Lake, and then we're going to be off trail from here all the way up to here.
Wow, okay.
It's about 5 miles.
All right. And then we're going to have, both Hans and I have these GPS locator devices. So we've got our first payload, Aurora 1, that we're going to go recover and track. We are going to use these snow machines to recover. We've got 2 expert guys that go track these for a living, sort of. One guy's a retired helicopter military pilot. And we've got GPS units, all the coordinates plugged in. We're about 26 miles from here as the crow flies. We're about 35 miles by trail, last 5 miles being really off trail, so we're gonna have to break some new trail.
The plan is to navigate well-worn snow trails and get within striking distance. But if the payload has landed away from the trails, they'll have to brave wilderness landscapes and deep snows.
Payload is marked with that dot.
Oh, so we are heading down south. We are on this road.
We're heading northwest.
It takes nearly all day to get to a point about 7 miles from the payload. Team members set out across hills and ravines. They get to within 2 miles. With time running out, they turn around.
It was too far away still to snowshoe in and snowshoe back and get back before dark. Not going to happen today. We're going to go back, recoup, probably send a skeleton team down tomorrow and try for a second recovery. Really disappointing we couldn't get there. You know, I feel like we're so close. This thing came 50 miles from the initial launch site. It was floating around in the atmosphere for 10 hours.
Right, I know.
And, you know, it's so frustrating just to get within 2 miles.
Oh.
The next day, a long hike on snowshoes finally gets them to the payload. Later on, they'll say it was worth the effort. One of Ben's goals is to help boost a whole new approach to space travel that's now emerging. May 2012 marked a major milestone in the rise of free enterprise in space. The SpaceX company successfully docked an unmanned space capsule with the International Space Station. It followed that up 6 months later with the first commercial resupply mission.
And launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
That's just the beginning. NASA is looking to companies to supply orbital launch services and to be long-term partners in future manned missions beyond the moon. Hoping to make big bucks, companies are developing orbital habitats and space planes, laying the groundwork for missions geared to mining, exploration, and even tourism. To Ben, this new race to space will go to the swift and the innovative. Today, because of weather and winds, he and his team have chosen to launch their payload from the spectacular Ruth Glacier in Denali National Park. Amid the rugged terrain, this immense river of ice sweeps down into a perfect natural runway. The payload and frame have been pre-assembled. The team makes a few last-minute adjustments. They inflate the balloon with helium gas. With dusk approaching, balloon and payload are ready.
Beautiful sight.
Got positive buoyancy. Both GPS devices are on and locked. Last camera check. Do a pan of the team.
Off it goes. The balloon drifts up through the dense polar air. With night falling, it rises up to the edge of space. Meanwhile, overhead, a solar storm is raging. Aboard the International Space Station, astronaut Don Pettit is making observations to complement what Ben's team finds. He passes over the Arctic several times during the balloon's flight. The auroras he photographs are an indicator of the amount of solar particles that will pummel Ben's rocket components. This is a time of high solar activity, approaching the peak of an 11-year cycle. The Arctic Circle is framed by a ring of dancing auroral lights. Curtains of green and red and blue drape our planet's graceful curve. This university-based experiment operates on the remote edge of modern science, dominated by large international projects such as the Hubble Space Telescope, the International Space Station, or the Large Hadron Collider.
So this technology that we're trying to miniaturize is significant in the sense that it sort of opens up new frontiers in the same way that miniaturizing computer technology to a point where it fits in your pocket. So everyone carries around a cell phone. They have these miniature computers. It does a lot of data processing. It gets you to your destination by GPS. That sort of technology didn't exist 20 or 30 or 40 years ago when you had these big mainframe computers that were at national labs. So we're trying to change the paradigm of space exploration from the national lab case to the cell phone case, the miniature case, to be able to do a lot more things and improve our capability as a species.
Working small, Ben's team believes they are onto something big. Their goal is not only to open new avenues of space exploration, but to actually seize the initiative. It's a romantic idea of individuals challenging the odds and striking out to new frontiers. With technologies that are getting smaller and more powerful, the obstacles to private space exploration appear to be falling. Who will hold back this new breed of explorer? Interstellar flight is part of a long-standing quest to expand our horizons and go where we've never been. What imperatives will define our first interstellar mission when it finally launches and finally arrives? Of our galaxy. They have identified 3,841 planetary candidates. Nearly 1,100 have been confirmed. The vast majority are Neptune or Jupiter-sized planets that orbit close to their parent star. By one recent estimate, based on data from the Kepler Space Telescope, our galaxy has 9 billion stars with planets roughly the size of Earth, with conditions that could support life. nearest possibility is a three-star system called Alpha Centauri at 4.37 light-years away. It's the brightest star in the southern constellation of Centaurus. Proxima Centauri, a red dwarf, is the closest of the trio, but so far no planets have been detected. Alpha Centauri A is slightly larger and more luminous than our own Sun, while B is slightly smaller. A team of European astronomers working at the European Southern Observatory in Chile recently detected a subtle wobbling in the light of B. It could be a sign of tugging from a planet's gravity. If a planet is there, it literally hugs its parent star, with an orbit that's even closer than Mercury is to our Sun. It's probably molten, with surface temperatures in excess of 1,000 degrees centigrade. Are there other planets far enough out for liquid water to flow? That prospect is the subject of intrigue in science and science fiction. Alpha Centauri is the fictional location of Polyphemus, a giant gas planet, and its moon Pandora, from the movie Avatar. The year is 2154. Earth has been ruined by environmental catastrophe. Greedy prospectors board the hybrid fusion antimatter spaceship, Venture Star. They descend on an innocent hunter-gatherer people called the Na'vi. Could such a place exist this close to home? One problem with Alpha Centauri is that the orbits of A and B bring the stars as close as Saturn is to our Sun. This means that planets further out could have been pulled away and flung out into space. For this reason, Alpha Centauri was not a high priority for planet hunters. That is, until similar examples turned up, such as Kepler-16. 16b is a planet that orbits two stars, which in turn orbit each other. Or Gliese 667, a triple star system 22 light-years from Earth. 667c is a red dwarf. A pre-Apollo project called Orion called for a series of controlled nuclear explosions to propel a spacecraft to high speeds. The project died amid concerns about the impact of nuclear explosions on the environment. Back in the 1970s, a group of scientists unveiled designs for Daedalus. This giant fusion-powered craft would have had to carry the plan. It's so powerful that a mere 10,000th of a gram is about all it would take to send a spacecraft to Jupiter. Current designs for an antimatter drive use magnetic fields to isolate and channel the fuel. The idea is to merge a stream of protons with a stream of its antimatter opposite, antiprotons. A magnetic field pinches or compresses the combined streams into a narrow beam. Annihilation, then, produces an ultra-high energy laser that shoots out the back of the craft. That causes a recoil effect that pushes on the magnetic field produced by the beam and propels the craft forward. Antimatter can be produced on Earth in giant physics labs like the Large Hadron Collider. Here, scientists accelerate atoms to nearly the speed of light and blast them together to release their fundamental constituents. The yield is so small that the cost of producing just a gram's worth of antimatter would be upwards of $100 trillion. And the stuff is so volatile that storing more than a few atoms at a time remains a significant challenge. Now throw in environmental impacts like rising sea levels, or the spread of deserts linked to a gradually warming climate. No matter how you look at it, our world is changing in ways that will impact the way we live and relate to each other. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the effects of war, natural catastrophes, or political upheavals? The technology needed to launch a first interstellar mission is certainly decades away. The actual journey will relay basic information on a world whose
its home is a real place, Alpha Centauri, the brightest star in the southern constellation of Centaurus. At 4.37 light years away, it's part of the closest star system to our Sun. Alpha Centauri is actually two stars, A and B, one slightly larger and more luminous than our own Sun, the other slightly smaller. The two stars orbit one another, swinging in as close as Saturn is to our Sun, then back out to the distance of Pluto. This means that any outer planets in this system, anything beyond, say, the orbit of Mars, would likely have been pulled away by the companion and flung out into space. For this reason, Alpha Centauri was not high on Planet Hunters' lists until they began studying a star 45 light-years away, called Gamma Cephei. It has a small companion star that goes around it every 76 years. Now it seems it also has at least one planet. That world is about the size of Jupiter, and it has planet hunters excited. Perhaps 2/3 of all the stars in our galaxy are in so-called binary relationships. That means there could be many more planets in our galaxy than astronomers once assumed. At least 3 teams are now conducting long-term studies of Alpha Centauri, searching for slight wobbles in the light of each companion star that could indicate the presence of planets. If they find a planet that passes in front of one of the stars, astronomers will begin intensive studies to find out what it's like. One of their most promising tools will be the James Webb Space Telescope, scheduled for launch in 2014 or 2015. From a position 1 million miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. The largest space telescope ever built, it will offer an extraordinary new window into potential solar systems like Alpha Centauri. With its infrared light detectors, this telescope will be able to discern the chemical composition of a planet's atmosphere. And perhaps whether it harbors a moon like Pandora. One prominent planet hunter predicted that if a habitable world is found at Alpha Centauri, the planning for a space mission would begin immediately. Here's that star duo seen by the Cassini spacecraft just above the rings of Saturn. To actually get to this pair of stars, you'd have to travel as far as the orbit of Saturn, then go another 30,000 times further. Or put another way, if the distance to Alpha Centauri is the equivalent of New York to Chicago, then Saturn would be just 1 meter away. So far, the immense distances have not stopped us from launching missions into deep space. In 1977, the twin Voyager spacecraft were each sent on their way aboard Titan III Centaur rockets. After a series of gravitational assists from the giant outer planets, the spacecraft are now flying out of the solar system at about 40,000 miles per hour. They're moving so quickly that they could each whip around Earth in just 45 minutes. Twice as fast as the International Space Station. Voyager 1 has now traveled more mass than is in the entire visible universe. While only a very tiny percentage of NASA's budget goes to advanced propulsion, there are some promising ideas on the drawing board. Rockets powered by nuclear fuel, or plasma, a supervolatile gas. Huge sails pushed along by the pressure of photons from the sun. Ion drives. But to reach Alpha Centauri within a human timescale, we'll have to go with the most potent fuel in nature that we currently know. It's the science fiction fuel of choice, antimatter. In James Cameron's Avatar, hybrid nuclear fusion and antimatter engines power a mile-long interstellar spaceship. At a speed of 670 million miles per hour, this vehicle makes the journey to Alpha Centauri in just 6 years. Antimatter really does exist, as the mirror image of the universe we know. It consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, The two annihilate each other in a ferocious blast of energy. Large amounts of antimatter were created and destroyed in the fiery dawn of our universe, the Big Bang. But somehow, in one of the great mysteries in science, we were left with a universe whose visible substance is almost all normal matter. The universe still produces antimatter through powerful collisions, such as a jet from a black hole slamming into a cloud of gas. When matter and antimatter obliterate one another, they emit gamma radiation that we can then detect with instruments such as the Fermi Gamma Ray Space Telescope. Fortunately, black holes aren't the only way to generate antimatter. In giant labs, like the Large Hadron Collider, scientists accelerate atoms to nearly the speed of light and blast them together to expose their fundamental constituents. Small amounts of antimatter can be made this way, but it's incredibly expensive. With a dedicated facility, the cost of producing it might come down far enough to produce usable amounts. And that's the hope of one researcher. Dr. Gerald Smith has been working for over a decade to find a way to trap this volatile substance and store it in isolation from the rest of the universe. Smith and his colleagues have designed a trap the size of a cigar case. It sits within a tank filled with liquid nitrogen and liquid helium, designed to cool it down to 270 degrees below zero. Once injected into this trap, antimatter particles are suspended by magnetic fields within a vacuum as empty as deepest space. But the problem is that anti-electrons, called positrons, tend to repel each other explosively. That makes it tough to store more than a few at a time. This team now believes it may have discovered a pathway to storing large amounts over longer periods of time. Their solution lies in combining positrons with electrons, forming an element called positronium. In theory, with the right magnetic fields, these electrically neutral atoms might be held indefinitely. When released under controlled conditions, ultra-high energy antimatter beams could turn out to be ideal cancer killers, or lead to revolutionary industrial applications. Or perhaps one day, they could power long-distance spaceflight. It wouldn't take much. Antimatter is so potent that it defies common sense. A chunk the size of a small coin could propel the space shuttle into orbit. Smith estimates that once in low Earth orbit, a human mission to Mars would take as little as 10 milligrams worth. The basic idea of an antimatter rocket is simple. A beam of positrons is released into the engine core, where it annihilates the surface of a metal plate. That creates an explosion that propels the craft forward. Another design uses a sail. A cloud of antimatter particles reacts explosively to its surface, propelling it forward. Short of traveling to another solar system, there may be good reasons to contemplate developing antimatter propulsion. A preliminary mission would speed beyond the orbit of Pluto, sending back close-up images of dark planet-like objects that ring the solar system out in the Kuiper Belt. longer distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample particles that make up the interstellar medium, or send back unique data sets on dark matter, the invisible stuff that makes up the overwhelming portion of our universe. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to gradually accelerate to around 10% the speed of light. That's 67 million miles per hour. It would then gradually decelerate as it approached its destination. At those speeds, hitting even a grain of dust could destroy the spacecraft. So it might be best to slow the journey down to a century or more. It's safe to assume for now that we would only send a probe to Alpha Centauri if we discovered a habitable world. There may be other choices in our solar neighborhood. They include Proxima Centauri, a red dwarf star 4.2 light-years away that may be gravitationally bound to Alpha Centauri. Beyond that, not quite 6 light-years away, is Barnard's star. Or there's Lalande 21185, a red dwarf 8.3 light-years away. We already know it has 2 Jupiter-sized planets. There are at least 22 stars within 12 light-years of Earth. And any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peaks, to push ourselves past our perceived limits, seems to be a vital part of what makes us human. Yet, explorers of old set off not just because it was there. At times it was greed, hunger, fear, or despair that propelled them outward from their homelands and allowed them to endure their long journeys. Whether we attempt to make this leap to the stars may come to depend on how we regard this planet. To the physicist Stephen Hawking, the journey is imperative. I don't think the human race, he said, will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet. Indeed, we can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But today, we can see the often conflicting trends that could one day propel us out into the interstellar void. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing rate at which numbers of transistors can be placed inexpensively on computer microchips has become a metaphor for the advance of all technologies in this century. From a few thousand transistors on the first printed circuits of the 1970s, computer chips now have billions etched onto their surfaces. Even that number could seem amazingly small in another few decades. Many observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. On the other hand, major periods of scarcity may loom. In the 20th century, the world saw the largest increase in its human population, from less than 2 billion up to 6 billion. The world world's population is now around 6.8 billion. It's expected to reach 9 to 10 billion by the year 2040, with the biggest gains in Asia and Africa. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. The scarcity of just simple clean water in some regions is already frightening. Now throw in environmental impacts, like rising sea levels, or the spread of deserts linked to a gradually warming climate. The culprit, to most scientists, is rising emission of greenhouse gases like carbon dioxide since the start of the Industrial Revolution. This map charts rising temperature readings from the year 1885 through to the present. In some places, they've gone up by as much as 2.5 degrees Fahrenheit. Computer models project the trend out to the end of this century. Depending upon population growth, energy use, and conservation, temperatures could rise anywhere from 2 to 11 degrees more. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the impacts of war, natural catastrophes, or political upheavals? No doubt, if or when we launch our first mission beyond this solar system, the occasion will spur reflection on who and what we have become as a people, as a planet, just as the first missions to the moon and our neighboring planets once did. At first, we'll send a probe designed to relay basic information on what's there, on a world whose light we have only studied from afar. As this cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness and prosperity, or of mere survival. When it arrives, we'll scan the data for evidence of a world like our own.